So now I'm going to talk about section 8.2, testing a claim about a proportion. So this will be our first actual hypothesis test of many, many hypothesis tests. Okay, so in order to test a claim about a proportion and see if we have evidence to support that it is changed, we have to have a simple random sample. No surprise there. The conditions for a binomial distribution are satisfied. The reason for that is any binomial distribution can be approximated by the normal. So that's what it says for number 3. And that's what allows us to use the normal distribution to find the critical values, those z-scores that we were talking about back in chapter 7. So all that it means here and here is n times p and n times q need to be greater than or equal to 5. And that just means you need to have enough successes and enough failures. And that just means, whatever kind of data you have, you need to have 5, you have to have an n that has at least 5, like whatever success is, and 5 of whatever failure is. So I'll mention that in an example. So as we already said, you want to have, in order to test a claim about a proportion, a valid random sample. And then we've really already mentioned this in section 8.1, but we'll be more specific now. That H naught is always going to be the same. P equals P naught. That's just some number. That was kind of the old idea. And you can have 3 options, and these are the ones that we talked about. Either your proportion is less than P naught, it is equal to P naught, or it's greater than P naught. Those are the 3 options for the alternative. You also need your level of significance, and this is typically given to you within the problem. And remember, that's the probability of a type 1 error. So that's why we need it, because we have to be willing to, say that there's some probability there and what we're willing to accept. The test statistic looks like this. So the test statistic I'm going to denote by Z star. So I'm using the word star here, Z star. And it just separates the test statistic from the critical value. So it is, however, a measure that is in terms of Z. So it is your sample proportion minus your proportion from the old idea divided by P, Q over N, and then the square root. So that's your test statistic. And so really what it's looking at is how far apart are P and P hat, and how far are they in terms of the idea of standard error, which is what you have in the denominator. Once you have that, that's your test statistic. Then you find your critical value or p-value to check against it. And what we'll be doing in this course, and this is specifically for my class, is my focus is always going to be on the p-value method for all of chapter 8 and all of chapter 9. So I won't be talking about the critical value method, because the p-value method, and you can read this in your book, is used a lot more nowadays. Critical value method is not used nearly as much. From having step 3 and step 4, that's what allows us to make a decision. And that's, what I'll be talking about here. Okay. So we saw this in section 8.1. So notice we have the idea of the left-tailed, two-tailed, or right-tailed tests. I'm just going to go like this, just to let you know that we do not use the critical value method. My class does not. I will be focusing on the p-value method. So the p-value is just a number. It is a probability. And specifically, it's the probability that we could get this new data that we got by chance without it actually being valid data. And that's because you could have very extreme, p-hats that come out, but they're very unlikely. So what we do is we just compare them, and this is what you're going to focus on here, is we just compare the p-value that we get to the significance level. And the big idea here is that the smaller the p-value, the better your evidence. So the way that we say this to help students remember is if the p, and that's p-value, and I know there's so many p's in this class, but if the p is low, the null must go. And that means that we're going to reject the null. If the p is high, the null will fly. And that means we fail to reject the null because we feel like the null is valid. The null will fly is just a term meaning the null is okay. Or at least we don't have sufficient evidence to support the alternative. So that's something to just remember at Rhymes to try to help students. But that is what we'll be looking at, and we'll see plenty of examples. Here's our first example. Okay, so notice I moved my normal distribution just to a different spot, and that was simply so that you could, see me in the corner wherever I'm going to show up. All right, so according to the Census Bureau, so of course we are doing the census right now, 8.8% of the U.S. population had no health insurance coverage in 2017. So this is our old idea. But now a recent sample was taken, 1,200 Americans, 130 of them had no health insurance. Use a 0.02 significance level to test the claim that the current percentage of Americans who have no health insurance coverage is greater than 8.8%. Okay? And then we'll always be writing the p-value method here, but other people use these same notes. Okay, so let's take a look at this example. So we start with the null and alternative. This is the old idea. And the old idea said that the proportion was 8.8%, written as a decimal, 0.88. Now remember, from section 8.1, these two things are all that's the same. The only thing that's different is that one piece in the alternative, and that's based on what you're testing. So notice that it uses the words is greater than 8.8%. So that's telling us, okay, here we go. Is it greater than 8.8% now? So is the true proportion greater than 0.088? That's what we're trying to test. Now, one thing that I do encourage students to do is over on this side to write their sample evidence. And what we're given is that we had a sample of 1,200 Americans, so that's our N, that's our sample size. This is still like the same notation from chapter 7. X is how many of them had no health insurance. So notice if we're thinking about the number of successes and the number of failures, here success is the number that had no health insurance, so that's 130, and then the complement of that, which is close to 1,100, have health insurance, and that's technically a failure just in the scope of this problem. So we have that, and then we're also told what else? We have our X and our N, and that will give us our P hat, which is always X over N, and that is going to be 1083. Okay, and so far so good. So notice it is bigger. That is bigger than 0.088, but we want to know, is it strong enough, depending on how many people have been sampled and our significance level, to be able to say that things have changed, that this proportion now is greater. So now we do our test statistic, the Z star. And as you can see from the formula from the last page, we take our sample data, the P hat, we subtract the P from the old idea, and then we divide by the square root of P, which is 0.088, times Q, which is just 1 minus 0.088, and you can find that separately if you want. You don't have to put it all together. And we divide that by our N being the number of people that were sampled. So this is a measure of how strong our data is. Now, a couple things to pay attention to is if you put this all into your calculator, either use the fraction bar, or if you're trying to put it all at once, or put parentheses if you're putting that into your calculator, so that your calculator knows to do the subtraction before it does the division. So it's just following order of operations. So if you put that into your calculator, you can see what you get, but you should get about, I'm going to do approximately because I'm rounding, 2.48. Okay, so that's this like measure, and you might be like, well, how does that help us? So what we do is we do not think about the critical region because we're doing the p-value method. Our job is now to find the p-value, the probability that we could get that 130 people out of 1,200 saying that they have no health insurance and not have that actually be, the true proportion. So down here is just a standard normal distribution, and you can see that this is, like this. So here is where that 2.48 is, 2.48. And then what the p-value is it's just this amount of area right here to the right of 2.48. So the way to find that is you can do it a couple different ways. You can either do it in the calculator or you can do it in the tables, because this is a z distribution. So, the standard normal. So if you go into the table and you look up 2.48 on the positive side, what you're going to find is that that's going to give you area to the left. So it's a very big number if you look it up in the table. It's 0.9934. However, we don't want the area to the left. We want that little teeny area to the right. So we're going to go 1 minus because we want the area to the right. And so again, stuff that we've seen in the chapter 7 that we did. So 0.0066, very small number. Now the way to do this in the calculator is not particularly surprising. You would just use, normal CDF. So the p-value would just be normal CDF, and you would put in, your 2.48. all the way up to some very large number, and mean and standard deviation, and that's going to give you the value using the calculator. So either one is fine. I've got my calculator right here, I found it. So let's see what that gives us. So because this is a z-score, this is why I can use normal CDF, because that's what it's a part of. So 2.48, if I put in 1 E99 or some really big number, just big, 0.1, and I paste it, okay, I'm going to get, not surprisingly, 0.006, and then, to 4 decimal places, 6. Same exact thing using the calculator. So either one is fine. Just make note of where you're finding it so I know how you're getting your answer. But the big idea here is that this is the p-value. This is that value that tells us how big the probability is that we could have gotten that kind of data by chance and not have it be the true proportion, or at least, strong enough to say something about the alternative. So now the only other thing we need to do is make a decision. So the decision about the null hypothesis just comes from comparing your alpha with your p-value. And that's from one of those first pages. So what I mean by that is you have your p-value, which is 0.0066. You have your alpha, that's from them telling us that the significance level is 0.02. And then your job is just to decide which one is bigger. So you do have to know enough about decimals to know which of those values is bigger. We can see that 0.02 is bigger than 0.0066. So what that tells us, and this is the kind of thing you'd want to write on quizzes and exams, you got to show me that which value is smaller. What this tells us is that the p is low. The p-value is low. And the rhyme says, if the p is low, the null must go. So that means that if you're remembering your decisions from section 8.1, we reject H naught. And again, there's only two options: reject H naught, fail to reject H naught. Then we write our conclusion. Now our conclusion is based on two things, and that is the decision that we made, as well as what our claim is. So let me come back here and just show you another thing to kind of think about, because we're ready for our conclusion now. But notice that the claim is that the current percentage of Americans who have no health insurance is greater than 8.8%. So this is our claim. And what I mean by that is the claim can either be the null or it could be the alternative. It could be either one, because there might be somebody saying, I want to show that it hasn't changed. And somebody else is showing, like, I want to say it changed. So who's making the claim? Okay, so based on those two pieces, that the alternative is the claim, as well as the fact that we rejected H naught, we now write our conclusion, and they follow a very specific pattern. In this case, there is sufficient sample evidence to support the claim. And then at this point, you just take a look back at the problem and you reiterate whatever the claim is. So the claim is that the current percentage of Americans who have no health insurance is greater than 8.8%. So this would be our conclusion. And this is just so that some person off the street that we're talking to would be able to understand our answer. We wouldn't just be like, oh yeah, well, we rejected H naught. Okay, that's not going to work. So we would say something like this. And so the two pieces that might change is you might have there is sufficient sample evidence, or you might have there is not sufficient sample evidence if you don't reject the null. And then the other part is depending on what the claim is. So to support the claim. So those are the two pieces that can change. Otherwise, the rest of the sentence is always going to be the same. And we'll look at examples and you'll get it, I promise. Okay, last thing I'm going to do, and then I'll save the other two for a second video, is the idea of identify the type 1 error. So if you go back to 8.1, you want to remember that the type 1 error is when we reject H naught, but H naught is true. So now we just do that, but we write it in terms of whatever our H naught is. So we would say we reject the hypothesis that, and then we look at what our H naught is, which in this case is that the proportion is equal to 8.8%. So we reject the hypothesis that the proportion of Americans with no health insurance, is equal to 8.8%, when in fact it is. So we rejected it, but H naught was true. So it is 8.8%. Okay. Okay. Now, the type 2 error that we have, the type 2, is kind of the converse statement, more or less, kind of, sort of. But it is we fail to reject H naught when H naught is false. Okay. So now we just write that in terms of this problem. So, and it's always a mistake because that's the whole point of it, it's an error. So I'm going to say mistakenly fail to reject that the proportion of Americans with no, I know it's a lot, health insurance is equal to 8.8%, when in fact it isn't. That's low. It isn't 8.8%. And we'll see this again. It'll come back a little bit in chapter 9, but it's just the idea that no matter how hard you try, there is always the chance that your data is your sample data is some sort of anomaly. And so even though it's this data that you got, it gives you the wrong, makes you decide on the wrong conclusion, that is a possibility. So a couple more examples of this.